Okay, so I'm just going to go ahead and get started here. Good morning, and welcome to the Breakfast Bash for, what's the date? November 10th, 2015. We're going to continue on talking about different data structures this morning. And this is kind of where I am starting to get excited about the series because we're kind of moving on from very simple data structures and starting to get into like slightly more complex ones. And so today we're going to talk about a type of tree. So the first thing that the first type of tree that everybody basically learns about is a binary tree. And what a binary tree is it's just sort of like a list that can split at every node. So you can take one of two paths on each node, and you can either go left or right. And we store things in this manner. So that's basically all there is to it. You have a root node where the binary tree starts, and from there you can add on new nodes to the left or to the right, and continue on doing this. The nodes without any children, this is called a child. So I should back up with some nomenclature here. So there's the root node. These are nodes, and nodes have two children, a left child and a right child. And the node above, for instance, 10 here is also called the parent of 10. And any nodes without any children are called leaves. And that's kind of the standard nomenclature for this stuff. A specific case of a binary tree. So if we go back here, you can see that the structure of the data is just kind of random. There's nothing really interesting happening here. It's just a sort of random collection of numbers, but we can sort of make this more. We can make this more interesting and useful if we find some structure. So this is a binary search tree, and I'm not going to explain it yet, but I will explain it in a moment. But I'll leave this up for just a couple of seconds, just in case anybody wants to kind of guess as to what the structure of this thing might be. And we'll move on in a couple of seconds. Okay. So what's the difference between these two things? I mean, obviously they're different shape, but that's not really what I'm talking about. But the first one, really, like the relationship between the parent and child, or the parent and the left child and the parent and the right child, are non-existent. There's no relation between these two things at any step in the tree. And so it's sort of an unstructured thing, but they are still useful because we can build a lot of different types of other data structures using this, namely heaps use it, and there are several sort of generalizations of heaps in general, and we'll talk about those at a different time. But so what's the relationship between the parent and the child here? Or the parent and the two children, I should say. So the key thing here is that at each level, the left child of each node is less than the node itself, and to the right, the right child of each node is greater than the parent. Building things up in this way proves to be very useful. So that's what we're going to talk about for most of this talk. Just because binary search trees are typically they're sort of the reason that you learn binary trees. Binary trees in the general form have a lot more, you really have to give it some structure for them to become useful, and this is kind of the most obvious structure that you can give to a binary tree. I should note here that if you have an equal element, I think you just need to choose. I choose to either put it on the right or the left for that specific instance of the tree, and you just have to stay consistent. But it shouldn't matter which way you put it, barring that. I'm not even sure if you need to be consistent, but that's something to note. We can have duplicates in these things if we want to, so I wouldn't. Don't worry about that. So just like the rest of the data structures that we've looked at, we have a few operations that we can perform on this thing. The first one is insert. So if you remember, we have to keep that invariant that the left children of a node is less than the node itself, and the right child of it is greater than it, or greater than or equal to, I'll say. So how do we insert this thing into the binary tree that we have? Well, we have to first try to, we have to basically traverse the tree in such a way that we can find where to insert it properly in the fastest way. So to do this, we'll first look at the root of the tree and figure out what the relationship between the root node and the node that we're inserting is. So in this case, 13 is less than 14, which means that 14 is greater than 13. So we're gonna go down to the right, and then we're gonna compare with that node. So 16 is greater than 14 in this case. So that means that 14 is less than 16, and we're gonna go to the left. And now, since there's nothing on the left of the 16, we can insert it there, and we're maintaining this invariant. And we're done. So removal of a leaf node is extremely easy. You just literally just take it off, no big deal, very easy. But removing an internal node is a little bit more difficult, and I'm not going to talk too much about tree traversals here, but there are different ways to traverse a binary tree, or any tree really. And what it comes down to is really, do you want to visit? You can do sort of one of three things. You can either visit the node, then its left child, then its right child, or you can visit the left child, the node, and then its right child, or you can visit the left child, the right child, and then the node, or the node, then the left child, then the right child. But so the one that we want to talk about is when you visit the left child, then the node, then the right child. When you do this, you can find what's called the in-order successor of a node. And what that is just the, it's sort of if you look at a couple of examples, it becomes sort of intuitive. It's the leftmost leaf of the right tree. So in this case, it's going to be this 14. And what we do to remove an internal node is we swap the node itself with the in-order successor of the node, and then we delete it. So in this case, we're flipping these two things and then deleting the leaf in the way that we did in the slide back. And this should always work because the next in-order successor is going to fall between the root node value and the node to its right's value. And there are reasons for that that I'm not going to go into too hard, because analyzing this kind of thing just adds like an order of complexity that I don't want to deal with in these videos. But you can just trust me, and if you want to research that kind of stuff, go for it. So the big thing the big operation on binary search trees, the reason that they're so useful is because it makes search really easy, which you might expect from the title, or from the name of the data structure itself. So what we really want to find out is, does something exist in a set of data? And if we have a binary, if we have our data structured in a binary search tree, this is very, very easy. So, or it's very, very fast, and it's easy to find our answer. So let's go through a search for 14. So we have two key things. Basically, we have two separate branches that we can take, and we're maintaining this invariant that the left child of any node is less than the node itself, and the right child is greater than or equal to the value in the node. So we can exploit this to find a value in our data set very quickly. So we're going to walk through a step-by-step search for 14 here. Let's find out if you exist. So we're going to take sort of the same steps as insertion, except we're going to traverse the tree in the same sort of way until we hit the spot where that value should be. And if the value is not there, we can stop. So in this case, we have 13 is less than 14, so we're going to go to the right. And then we have 16 is greater than 14, so we're going to go to the left. And we find at that point, we have 14 in the value of the node, and that's exactly what we're looking for. So we found it. Yay. So let's look for something that doesn't exist. What do we do in this case? So we're going to follow pretty much the same progression here. So 13 is less than 15, so we're going to go to the right. And 16 is greater than 15, so we're going to go to the left. But at this point, there's one more step involved here. But when we see 14 here, we want to go to the right, right? So 15 is greater than 14, so we want to check the node to the right of 14, but there's nothing there. So that tells us that, we're done. There's nothing else to check. So 15 can't be equal to nothing, and therefore 15 does not exist in our data set. So big old no. Does not exist. So I just wanted to take a look here. When we have our data, the same data, structured in a binary search tree, to find out if something exists in this data set, all we have to do is 3 comparisons at maximum. So the root, and then the second level, and the third level. We never have to go up the tree, because we can just follow the path that we would expect the value to be at if it were in the data set. And this is very important. So if we look at, for example, a singly linked list, which we looked at the other day, in this case, we have a maximum of 6 comparisons. So if we're searching for 100, we're gonna 1, 2, 3, 4, 5, 6 comparisons. Or if we're searching for something that doesn't exist, we have to traverse the entire structure. In this case, traversing the entire structure is it's half as hard. And this is already on a very small data set. And you can imagine that once this gets bigger, this data set gets much larger, the performance gains are immense. Instead of traversing everything, you're traversing only a very, very small subset of the the nodes, because you have a path that the node must exist at if it existed. And so here, this is just, yeah. So on average, in this linked list data structure here, we have an average of n/2 comparisons. And by the way, I'm being a little bit hand-wavy here with this analysis. There are some constants involved and other stuff, but I'm just kind of trying to get to the core of what I'm talking about. So on average, we have n/2 comparisons for a data set of size n. So we have an average of 3 comparisons because either, and that's if we search for something in here. But you know, if we're searching for 13, we only have to do 1. If we're searching for 100, we only have to do 6. And so somewhere at some point, you know, you get an average of 6 comparisons, or of 3 comparisons, plus some constant. But in our binary tree, we have an average of log base 2 of n comparisons. So again, a little bit hand wavy. There are some constants here that I'm dismissing, but we'll talk about that another time. But sort of, kind of, on average, we have log base 2 of n comparisons. So log base 2 of 6 comparisons is 3, if I am correct. And so, or it's about 3. And so in this small data set, we can sort of see what that means. But what happens when we bump up the size of the data set to 1 million nodes? For the singly linked list, n/2 at 1 million is 500,000. So to find out if something exists in our set of 1 million data points, we have to do about 500,000 comparisons on average to find it. But with a binary search tree, actually log base 2 of 1 million is a little bit less than 20. So you can see how much of a benefit we get from this by bumping up the size of the data set significantly. On average, we're only going to be doing 20 comparisons for to find out if something is in our data set of 1 million points. And I think that's pretty cool. And I hope you think it's pretty cool too. This is one of the reasons that we study data structures at all, because at some point, when we get big enough data, we want to be able to traverse it in a quick way, and that's what we're doing. We're significantly reducing the amount of work that the computer has to do if we structure our data in a binary tree for ordered data. So there's a lot of hand waving in here, and this is sort of the first time I've encountered spots where I'm like, I don't know how deep I should go into the rabbit hole, and honestly, I couldn't just pull it out of a hat. So the next video, I think I'm going to start talking about computational complexity a little bit, so we can sort of put things in terms of big O, big omega, and big theta notation. Instead of having to say, on average, we're doing n/2 comparisons, but that's kind of a hand-wavy argument, we can just say it's big O of n and big O log n and move on. So that's what the next video will cover. I'll put that together for next week, and hopefully you guys enjoyed this one, and I'll see you next time. Thanks.